Welcome back to Chem 4300. In this video, we'll finish up Chapter 8 on classical wave motion, and we're going to look at a web app written by Paul Falstad that illustrates wave diffraction and interference in two-dimensional systems. So opening up the app, you should get something that looks like this. And what we're looking at here is the two-dimensional wave as it passes through the slit. So imagine a plane waves, two-dimensional plane waves, or line waves if you like, coming from the top of the screen and hitting this slit and then diffracting out. Now what we're looking at here is the intensity of the wave. If I click this, I'll look at the actual wave function, which is now time dependence. You can see the time dependence. And what we're seeing is that the green is the positive amplitude and the red is the negative amplitude. I'm going to increase the resolution of this, assuming you have a computer that's fast enough to handle this. And we'll get this pattern here. So this is a very nice illustration of the diffraction. The wave is coming through and it's hitting the slit and it's diffracting out. Now if I lower the source frequency so that I'm getting longer and longer wavelengths, eventually I get to the point where the wavelengths is on the order of the slit width, and you see this really massive diffraction pattern, which is sort of what I showed in the slide earlier in the lecture. Now, if I increase the slit width, then again you can see that if I go to the maximum I can here, there's this region here where it looks like the plane wave is just sort of coming through and is not too strongly affected, and the diffraction is out here on the outside. If I increase the source frequency, increase it as high as I can go here, then you can see that when the frequency, or in this case the wavelength, is very, very small compared to the slit width, then it just looks like the waves are just passing through. If I show just intensity here, it would, for example, if we were looking at light, which is a wave, but we had a slit width, which was too large compared to the wavelength of light, then you would just see a beam of light going through, and you could probably barely see this interference pattern here, or this diffraction pattern, I should say, out here, and so you wouldn't know that light has this wave-like behavior. So it was when Huygens could get slits that were small enough that he could actually see the diffraction-like behavior here. And you can see as I lower the slit width smaller and smaller, eventually you start to see the kind of behavior. I might have to lower the frequency a bit here to make that a little bit more obvious. So here you see the kind of behavior that is expected for waves as they diffract through, and even light, for example, would diffract through if you get the slit small enough. Let's switch over to two slits so we can look at constructive and destructive interference. So what I'm going to do is go back to a much lower source frequency, and I'm going to turn off the intensity and go back to showing the wave function. And I'm going to change the separation between these two slits. And here you see a nice illustration of a plane wave coming through, hitting these two slits and diffracting through the two slits, and as these diffractive waves come together, they constructively and destructively interfere, and you see these lines of destructive interference here in the output of this simulation. So this is a nice example of that we sort of tried to show, and I tried to show in the slides, of the constructive and destructive interference of waves. And again, we can try to see what happens as we increase the source frequencies. So going to smaller and smaller wavelengths here and increasing the slit widths. And I have the separation now, it's pretty full. And you see that there's not much sort of crossover of waves from this slit to waves of this slit. It's in this region here. There's diffraction of these guys, but there's not much constructive and destructive interference in this region here because there's not much overlap. So I'd have to move the two waves closer together before I can start to see pretty sizable constructive and destructive interference. And here you see that happening here. Now I'll leave the rest of this up to you. There's not much to show really here. You can look at multiple slits and sort of having it hit an obstacle, and so this is waves coming in and plane waves coming in from the top of the screen and hitting an obstacle and how that might look. But you can play with this yourself and change some of the parameters here and get a better idea how this interference and diffraction behavior occur.